All right. Well, good morning, good afternoon, good evening to everybody for joining us on this DSIAC webinar. We're happy to have Rick Lazetsky here to share about the shielding system. Before we get going, I'm going to do a quick intro video to DSIAC, give a few pointers about logistics for the webinar, and then we'll launch into the presentation. So without further ado, I'm going to go ahead and make sure we are sharing a video that we will play.
Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense systems DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
All right, very good. Thank you all for watching that video. Hopefully it came through okay. I know there's a bit of a lag. I'm going to bring up now the slides for Rick, and apologize for the delay here. All right, and Rick, you can just be a quick check. You can see those slides?
Yes, I can.
All right, good. Well, before we go ahead and launch into Rick's presentation, let me just give a couple pointers about the webinar platform. So what we're going to do here is just have Rick deliver the presentation all together, and at the end we'll have a Q&A portion at the end. So any questions you have during the presentation, at the end of the presentation, please go ahead and get them into the Q&A portion of the WebEx platform. You should be able to find them by clicking the 3 ellipses on the bottom right of your browser screen for WebEx. There's a Q&A section you can click on. You can enter your question and get it in queue that way. There's also a chat, so I just want to distinguish between the chat and the Q&A. We'll do our best to kind of moderate both of those and make sure they all get in the queue for the Q&A. But please, again, check out those double ellipses, Q&A, and you can get your question in there. If you have any technical issues along the way, first off, rest assured we will be recording this, so we'll make that available and you can check that out later on. But also, if you have any issues, you can dial in and we'll drop the dial-in information. It should have been part of your registration. And you can download the slides from the webinar webpage and follow along that way if that's any easier. So I think that covers the basis for the logistics of the webinar. So I'm going to go ahead and hand it over to Rick Lazetsky. So Rick Lazetsky is a subject matter expert with service engineering with the Aberdeen Research Operation. He has over 40 years experience with vertical lift aircraft and has spent most of his work on composite materials and survivability technologies to improve platform performance. He has more recently been engaging in efforts that he's going to speak to today about multifunctional composite materials with structural and integrated electromagnetic shielding capabilities. This has been demonstrated, as he'll go through, on some electronic enclosures and is expanding to military platform structures as well. Rick has been previously employed with Boeing for a number of years and holds two patents for autonomous self-sealing fuel bladders. So with that introduction out of the way, now, Rick, I will hand the mic over to you, so to speak, and you can just tell me when to flip slides from here.
All right. Sounds good, Brian. Thank you. Just a little additional background. Recently, we've been doing a good bit of work, as Brian stated, with electromagnetics and composites. So this presentation is focused on looking at what the current, I'd like to say, state of the art or direction has been with shielding with composite materials, and then of course indicating what we've been doing with this multifunctional material. So next. So the kind of things we wanted to cover is what are the potential electromagnetic threats. Excuse me. Current shielding approaches for electronics. The getting into multifunctional materials. Discuss a little bit about manufacturing and fabrication. There are some things we've seen in that regard. And then talk about repairability and the future direction for these type of materials. Next. So what are the EM threats that we're typically dealing with? They range from both natural and man-made. You can see some of the examples on the right. Frequency ranges, there's a broad set of frequency ranges that are actually covered. And for each of these, whether it's EMI all the way through HPM, the table shows what frequency ranges are associated with, and the EM shielding range that's required to basically provide protection against those particular energies. Granted, emerging threats in electronics may require more, but right now the focus is on these basic three areas, if you will. Next. So where do they actually come from? The EMI, EMC, that can be lightning, electrostatic discharge, solar flares. You have civil in terms of cell towers, generators, high voltage lines, and then military, there is jammers, installed electrical equipment. And what I mean by installed electrical equipment, that within the electronics bay of military equipment, you've got different types of energies, if you will, associated with the electronics that are in there, and they can actually interfere with one another. For EMP, there's the lightning. That's there's also again, we start looking at coronal discharge, things that occur within the universe, if you will, in our solar system. For the civil, there's circuitry, motors. But when it comes to military, we're talking about nuclear EMP, also NEMP, non-nuclear EMP. And by the way, EMP is electromagnetic pulse for those who are unfamiliar with that. And then finally, we have high power microwaves. Natural, you're really not going to see that too much effect unless you get into things like a supernova, coronal discharges, things along those lines. But from a civil aspect, there are high power radars. And for military, there is backward wave oscillators and in particular directed energy weapons, specifically designed to provide high power microwaves to knock out the electronics. Next. For those who might say, well, geez, are these threats real? Well, they are. Here's some examples. Here is a Russian Krashuka 4 mobile electronic warfare system. This is one that was operational since 2014, and they did indicate that it did kill a Israeli F-35. You also have the 22PP for aircraft. It's operational since 2018. Chinese have mobile ground systems, and there's also EW jet as well for providing jammers to disable radar. So they are real. They are out there from a military aspect. Next. So when we talk about shielding techniques, just what are we dealing with? And the shielding effectiveness is the definition that is used to determine how effective a system is in defeating electromagnetic radiation, and it's a ratio of radiated power without the barrier to power received with a barrier. Typically, an incident wave will strike your material. A certain amount will get absorbed, and a certain amount then gets reflected back, and then the remainder then gets transmitted. You can have re-reflections occurring within the area, if you will, or within your barrier. And that's really dependent upon how that barrier is constructed. We'll talk a little bit about that, I think, in a few slides. Re-reflection can actually hurt you because you can actually get the re-reflected wave can come back, and that can actually cause a decrease, if you will, in your shielding. So you have to balance how this barrier is actually constructed, both in thickness as well as the inner layers, if you will, the composite. Next. So the barrier characteristics for impacting shielding is barrier thickness, electrical conductivity, and the magnetic permeability. And then in addition to that, you also have the construction of the enclosures. That can be shaping, and penetrations actually turn out to be something that is very critical. You have to make sure that the container that is in which the electronics are housed is sealed. Otherwise, you can actually get leakage, and no matter what your material is, if you have holes or penetrations within there, you can actually lose the effectiveness of the shielding. This in turn makes seals quite important. We use elastomers with conductive fillers, and then also how do you actually integrate it with a platform? There are some areas you will see, since the typical materials have been metals, where they have very complex shapes, if you will, might not be very conducive to a composite. But the composite being much lighter, we can get away with a straight box, fewer penetrations, fewer holes. There are some things you do still have to worry about, such as cooling, vent holes, things like that, but you don't want to have the holes of just associated with assembly causing an issue for your electromagnetic shielding. Next. So this is what we talk about when we talk about platform integration. You need to accommodate heat sinks for cooling and venting. Several examples are shown. In the lower image would be a fixed wing aircraft, and there is an avionics bay which is filled with electronics. That is even more apparent in the image in the middle at the bottom, which is that for a helicopter, where the electronics are isolated in single areas, or whenever possible, they're isolated in a single area, protected with racks, and then protected with enclosure boxes. The typical way of doing that is an enclosed metal box, but these metal boxes, they tend to be quite heavy, and that's where the composites have been coming into play. Is if you can get the conductivity up sufficiently, then you can lower the shielding. It's also a lot better for stacking within the electronics rack. You notice the two images, the image up on the upper right, and then right below that, the upper right is showing fins, if you will, or channels that are cut out for heat dissipation, and then the other one is the installation of fans. So this is where we talk about how do you actually work your penetrations in without degrading your electromagnetic properties. Next. So what kind of shielding techniques have been explored? You may hear a lot of these. We know that the metals, typically copper and aluminum, and this also includes coatings and plating. This seems to have been, we'll call this legacy, if you will, the most common. There are carbon allotropes used as fillers. That's exfoliated graphite, graphene, carbon fibers, carbon nanotubes. There's been a lot of work going on in those areas. The filler materials both provide strength and conductivity improvements to the composite, and they also operate through the development of multiple reflection mechanisms. If you can imagine a series of small tubes suspended within your composite matrix, there's a lot of areas for the electromagnetic waves to be both absorbed as well as to be reflected and re-reflected within the structure. One other area where there has been some work is intrinsically conducting composites, and that is really done based on the chemistry, if you will, the composite itself. And this is usually used as a component to a composite with the addition of metal nanoparticles and carbon filaments. So it's not typically done by itself. Interesting thing with all of these additives, if you will, when we're talking about the fillers and allotropes, things like that, is typically they're going to go into a composite material, which is, say, injection moldable. So really you're putting it into a resin system and then injection molding it into a component of a certain configuration. Next. Because of that process, you don't really have as much control over how these fibers or how these additives are going to lay. As such, the shielding solutions wind up being quite limited. Metal enclosures, we look at approximately 1/8-inch thick aluminum. We can get greater than 80 dB, between 10 megahertz to 100 gigahertz. It's a heavy approach, has limited applications, obviously because of the weight of the box. You can be looking at a box that can weigh 70 pounds, multiply it times the number of boxes. And if you're putting this on something like a rotary ring vehicle where you can't afford any of that extra weight, it becomes very impactful on the performance, if you will, of the vehicle. Non-metallic enclosures, using the techniques that I mentioned earlier, they are more weight effective, but typically only levels between 30 and 70 dB. This is out of a DSIAC search. That seems to be about where they're at. This includes materials added to increase the electromagnetic shielding effectiveness. So it's not just a graphite reinforced plastic, but it's also those that have these other additives in there as well. As a note, there is an aircraft platform out there that once it was fabricated, if you will, it's even lower than that. We typically saw 30 to 50 dB in the electromagnetic shielding associated with the structure. So gets a little bit sporty or tricky, however you want to put it, in order to actually develop your shielding that will appropriately shield your electronics in a given platform. Next. And just to mention briefly that this is why there's been somewhat of a focus on the multifunctional composite, because anytime you do anything with parasitic weight, it becomes a big deal. So where do we go from there? We started out and we started establishing what the requirements are based on military specs. What is the minimum amount that's needed? And what we have used at service as a pattern is an 1/8-inch thick aluminum Air Force supply box that was supplied to us by the Air Force for a program that we were involved in. These are some of the spec requirements. The note here is that hemp was not included in the graph due to classification, but it was considered as we developed the requirements for which we were working towards with our electromagnetic material. Next. So what we came up with is, this is back on an Air Force SBIR program, electromagnetic hardened composite enclosures. We used as a base for the material graphite peak composite. We had to maintain the composite structural properties, and we had to establish the electromagnetic thresholds. So when we look at the Air Force baseline enclosure, it gave us 75 to 135 dB. And we had targeted a shielding effectiveness of 60 for a threshold. That was largely based on the spec requirements of the previous chart, with an objective of 80 dB as a minimum. And I do emphasize minimum because in both cases, the material we had developed far exceeded both of these values. Next. So in dealing with a multifunctional composite, the idea is that you want to be able to maintain the multifunctional aspect of it, in which case you are working with a system that provides structural characteristics, but also electromagnetic shielding. When you do this, the goal is a significant weight reduction. So in the case of what we were using here, we had the Air Force box that we were given for this particular program, weighed in at 32.5 pounds. We came in an electronic enclosure box of 7.6 pounds. So that's a 76% weight reduction, which is quite significant. And the chart on the left shows the trace between the AFRL aluminum enclosure and the composite enclosure. And at the lower frequencies, the composite enclosure actually outperformed, as well as at the higher frequencies. And the mid frequencies, they kind of flip-flop between each other. But generally speaking, we were always roughly above the, there's a couple dips, but we were always above the 80 dB. And if you were to just go on an average, we're probably averaging up around 100 dB shielding effectiveness. And that actually covers a large number of those HPM, EMI frequencies that you have to protect against. Some of the higher levels that are shown where you want to get even higher has to do with how close you are to an object, things along those lines. But in this case, we track quite well with the aluminum box. Next. The multifunctional material that we had dealt with was a graphite peak, and the graphite peak alone actually has a high electromagnetic shielding effectiveness, but we want to say that it's not necessarily just the graphite peak that creates that. It really has to do with how it's fabricated as well. We use a high compaction pressure with in-situ tape placement. So when you look at a composite material, think of it in this terms. Your graphite material represents a conductive layer, your resin represents an insulative layer, and if you have a large number of insulative layers compared to your conductive layers and you don't have a high enough compaction, you're going to get a structure that's going to be more exhibit a lower conductivity. Then if you have a high compaction and you get nice intimate contact between all the graphite, and that's basically what happens with this type of process. To further improve the shielding effectiveness, copper mesh was actually added into the structure. And in all cases, there were overlaps to provide for the conductivity. And the quantity layers actually defined resonance chambers. So in the earlier chart, we showed a single barrier. And I think on the next one, we might actually show what these resonance chambers look like. Next. Actually, I'm sorry, it's probably a little further on. This is just some more data. It shows that we have the AS4 peak with copper plies, and you can see that we can actually change the frequency response of the materials based on what the additives are, as well as where they're actually placed within the structure. And this is where we determine that what we have going on is because we have multiple layers of the copper mesh in there, we are creating resonance chambers, when that gives you multiple re-reflections within the structure, and that can actually help you to tailor your material to certain frequencies. Next. To demonstrate this, was just completed a shielded structure. It's a portion of a tail cone for a helicopter. That's what's shown up in the upper right. And the skin itself uses the multifunctional material to provide electromagnetic shielding, while the other elements in there, which are typical structural elements, happen to be of the the resin system. They are fabricated separately, and in a winding process, the outer skin is wrapped around a tool in which these other pieces are inset, and as such, the skin is then fused to these components. What that means is we talked earlier about not having penetrations. In this case, there are no fasteners required. When you are finished, you have a fastenerless section. We did something very similar for an unmanned aircraft, and that is what's shown in the lower image. They are actually a 2, 3, and 4 layer mesh structures. All of them obviously look the same because you're just seeing the outer graphite layer. We applied bulkheads to the inner side, and we made some measurements on those particular elements. The fuselage section, that is currently in the hands of the test facility now, so they should be starting tests on the electromagnetic shielding properties for that. Next. So when you look at the UAS fuselage, this one has been tested. It was an in-situ tape placement. We did use bulkheads 4 1/2, which were preformed, and they were done out of 3D printed and pressed. That represented the seal. Again, the idea is you have to seal your interior structure to preclude any leakage, if you will, of the radiation. There was an average of 60 plus dB in the 50 to 18 gigahertz range, and the way it was broken out is between 50 to 600. We were above 67, 1 gigahertz to 5 above 88, and 7 to 18 above 102. So this put us well above the threshold requirements for each of the 3 major threats we had defined earlier. And also we were able to get above the objective in most of those cases. Next. When I mentioned resonance chambers, this is what we're really dealing with. And this is the multifunctional, what I'm calling design observation at this point. Multiple laminate configuration. The copper colored areas represent the copper mesh. And what happens is you get this reflection and re-reflection going on. The thicker laminate enhances the shielding effectiveness at certain frequencies. And if you look at the overall performance across all frequencies, winds up being enhanced. The thicker laminate actually supports the separation of copper mesh, because the problem is if you get too many layers of copper mesh in there too close to one another, you lose your structural properties of the material. We found about the 3-plies and the thicknesses we were dealing with, which were quite thin, seemed to be adequate. There was some property loss, but it was considered minor. And in the case of the skins where we're dealing with shear, primarily shear loading, there was very minor impact, if you will, to that property. The thinner the laminate, it does affect the resonance. You're not going to get as much resonance going on. In any case, we still wind up with something that is lighter than the metal, as well as lighter than the general state of the art. This is a much more efficient structure. And the idea here is that you can now actually use the structure in the structure itself and not wind up having to put all of your weight into the electronic enclosure. So if you look at the electronic enclosure as being nothing more than parasitic weight for EM shielding, this EM shielding now is transferred to the outermost surface. And by doing so, you can actually even lighten that box up even more, because now you're just protecting the electronics from one another, not having to protect them from the outside electromagnetic generators. And then, as I stated, the copper mesh placement and the laminate we found is critical. This can alter the electromagnetic shielding effectiveness depending upon where it's placed. So if you place it close to the surface versus more in the middle, you will see your frequency dips and rises vary across the frequency band. Next. Manufacturing and fabrication concerns. It is configuration driven. Simple box configurations work best with generous radii. Complex shapes are difficult to fabricate, and they do limit the materials to injection molding or metals. And as was stated earlier, they are not giving the properties or not developing the properties that we have seen with this particular material and this fabrication technique. With a structure, the idea of transferring a portion of all of the shielding effectiveness to the external surface can actually benefit the structure. In which case the enclosures now only have to be then developed to protect between the electronics between each other, not worrying about the outward sources, if you will, of electromagnetic radiation. Some composite processes considerations are injection molding and the automated tape placement. And with the injection molding, you do want to minimize resin-rich areas, because anytime you increase the amount of resin, you're going to decrease your conductivity, and that's going to impact your shielding effectiveness. Automated tape placement, which we have been working with, has been demonstrated to support controlled placement of fibers and tailoring of the EM shielding effectiveness properties. We're actually able to run the fibers with pretty good indication of where they are. No resin-rich areas, no fiber wash, and as such, that even helps in some of the modeling that we've been trying to do as well. Next. Integration of special features, cooling fans. This is something we are currently investigating. There are some concepts we have on the board on how we can actually still have a mesh, if you will, to provide for the flow of air, and also then to provide some electromagnetic shielding, as opposed to just having an open grid, if you will, that represents an area for significant leakage of electromagnetic radiation. The same thing applies for enclosures and structural penetration, such as cables, other hardware, access panels. These are largely handled with conductive seals. And then finally, internal separations. And that's when you actually have your enclosure. How do you actually separate the electronics from one another within with inside, such as integrated electromagnetic barriers. We've been looking at some of the ways of actually doing that so that within the box itself, you can have individual barriers set up that help protect individual electronics from one another, but still allow them to be contained in the same enclosure. Next. For repairability, maintainability, you always have to worry about corrosion control. Obviously, metal structures, that seems to be something that should be quite obvious. However, when dealing with your composites, you have to worry about galvanic corrosion. Ultimately, the composite, if the composite is going to be connecting with a metal, there is a chance, since we have say a graphite-based material, we will have a condition where that could actually create a situation where a galvanic cell winds up being established, and you can corrode the metal to which it's adjoining. The way we get around that is we actually would use fiberglass, but now we're introducing an insulative layer in there. So you have to be very judicious about how the design, so that layer is only between your box or your structure and the metal to which it is touching. And then damage mitigation, you want to maintain your structural electromagnetic characteristics. Repair techniques are really not going to be any different, with one exception. You want to maintain your conductivity continuity. So where before you might just cut out an area, apply a patch, and bond it into place, you now have to deal with that interface between the two. And ideally, you want to try and get to the point where you actually have your conductive fibers, whether they're graphite, whether it's a coated carbon or it's a copper. You want them to be exposed, and you want to have the same thing on the copper mesh, so you get good continuity between the two to maintain your electromagnetic characteristics. And then you still have to treat it from the aspect of how to actually perform a structural repair. So your structural adhesives still are going to have to be the same, basically. Next. Future direction, this tells you the direction we're going, and it's really a recommendation for a lot of the work that's out there. We're exploring design options and the impact of them on electromagnetics. These include vents, thermal properties for cooling, electronic box spacing, for example. One of the things we're also considering is system coupling. That is to say, if I have a fuselage structure and I have use the multifunctional material to provide electromagnetic shielding, and then I have an electromagnetic shielded box on the inside, what is the effect on the electronics, internal electronics? And we do actually have a test scheduled where when we do test the fuselage section, it will be sealed off and tested by itself. But then there's going to be a secondary test. We have it's under a different program, but we are going to use the same fuselage with a secondary test, and we'll be putting a box in there that has a shielding as well to see how much lower that shielding can be driven to by having those two different layers. And then development of an analytical methodology. We have been working with ARL and University of Maryland to develop this tool. The initial development has made some pretty good headway in terms of predicting the electromagnetic features using just the graphite peak material. One of the things that we're also looking at is what happens with other resin systems. One of the things that we have found is that we have fabricated a material out of an 8552 IM7 peak. IM7 8552, and we actually compare the EM results of that panel with that of the IM7 peak, and they were pretty comparable to one another. When we look at an aircraft structure made out of the 8552 IM7, significant difference. The numbers are significantly lower in terms of shielding effectiveness. So that indicated to us that there is a factor associated with how this is actually fabricated, because when we fabricated the IM7 8552 panel, although we were using an autoclave, the process we used mimics that of a press. So basically high pressure, good compaction. You don't typically see that when you start dealing with your tools, and especially dealing with cloth and other materials that are required to fabricate with this particular material. So that's some of the areas that we're looking a little further into for development of both this material as well as some other areas that we're looking at for electromagnetics shielding. And I think that might be it.
Yeah, I think that covers it. I'm just going to jump to the title slide, so folks can make sure they get your contact information there while we're going through the Q&A. Let's see. So yeah, that was great. Thanks, Rick, for the presentation. And we did have a couple questions come in. Let me just remind everybody who's in the WebEx platform, there should be 3 ellipses bottom right. You click that. There's a selection for Q&A, and then you can enter your question there and get it in queue. So we had 2 questions in the Q&A, and then one that's in the chat as well that I'll just kind of pass along. So the first question, Rick, that came in asks if you could comment on the use of nano-sized metal particles that are dispersed or distributed by blending liquid or gaseous methods within the composite structure for uniformity of shielding and suppression of EM signature for electronics. And by the way, Rick, hopefully you can check out the Q&A yourself and read them, so you don't have to just only hear them audibly from me.
Okay. From what we have seen in that regard, the biggest problem is just that it is that even dispersion, if you will, within the resin. And the one thing that we do not see is we do not see the high levels of electromagnetic shielding. And I'm going to go back to that from I don't know if you want to flash up what is it, the chart where we show the level up. Go back up. No, the other way. There you go. This is the kind of shielding ranges that we're really looking for. We're looking at 60 to 100 dB, and for HPM, anywhere from 100 to 140 dB. And that's really what you're trying to focus on. So with a lot of these other materials, what we're seeing is you're only getting around that, 70, 60, 70, and even somewhere upwards of 80 dB. And at this point, I surmise that most of that has to do with you're just not getting the contact between those materials. Think of it in this term. There's actually something called percolation theory. And what the percolation theory deals with is as you work through a composite material, if you will, you have a conductive material and an insulative material. And you have to get to the point where you have so much conductive material in there and so much connected to one another that it begins to think that it's all conductive. It's kind of a peculiar way of looking at it. I haven't found anything that really defines how you can determine whether you are reaching that or not, but that seems to be one of the biggest things. And again, it's kind of breaking it down, almost using the rule of mixtures, if you will, in terms of how much resin versus how much conductive material you have in there. I don't know if that really answers the question, but that has been the biggest thing that I have seen, is just the inability to get to these kind of shielding ranges, at least what we have been addressing. Now, obviously, if you're only looking for 60 dB and you're looking down at the lower end of the electromagnetic interference and communications area, that may be sufficient. But for the military vehicles, we've been focusing at the much higher levels. We haven't been able to get up to 140, but we have gotten up to 120 dB. Now, when you talk about the higher levels, like 140, and you notice for each of these ranges, there is a range. A lot of that has to depend upon the power, how close you are to the, object that's emitting the radiation.
Gotcha. Okay, great. No, thanks, Rick. And I'm trying to stitch together some similar questions that have come in, but maybe I'll just jump to doing them chronologically. So, because the next question that came in was about the osprey tail that you showed on one of your later slides, which I'll try to run to. And the question was, is the helicopter tail section referenced in a previous slide applicable to the Osprey? And can you give details on the demonstration timeline? I want to say that was probably it.
Okay, now, that particular structure was based on the RA-866, the Comanche program. So it's that size structure. It's about a 3 foot. It's not 3 foot in diameter, but that's what the structure was based on, because that was the properties we had for the structural aspects of it. It can be applied, however, to any structure. It could be applied to the V-22 Osprey. but it was represented something that was smaller, and it is representative of a tail structure for a single rotor helicopter.
Gotcha. Okay. All right. Well, then getting back now in the order as they were received, are the next questions actually in the chat, but that's okay. We'll work it. It says, are the shielding results that are shown for a particular angle of incidence, or is the minimum across all possible incidence directions? I don't know which results are being spoken of here. Perhaps those. I'm not sure.
The tests that were done, the way it was done is we had a box, and I mean, it was non-directional. Basically, we had an antenna placed inside of a box emanating, and we had a source on the outside that was measuring the basically what was coming out. So, you know, we didn't focus in terms of any one particular direction. It would have been more of a
Omni.
Yeah, omnidirectional. Yes.
Yeah. Gotcha. Okay. Well, that helps answer one of the other questions, which asked if you could elaborate on how some of the shielding levels were tested. And I guess that, unless you have any more to add, that might cover it.
We had two basic ways, which and feel free, you can contact us directly. One of the things I know I mentioned earlier is a lot of this information that we have. Some of it we have to get customer approval to release it. Some of the other information might just be simply an NDA has to be put into place. But I can comment on the two ways that we actually have measured, both of which are acceptable per ASTM standards. The one of which is you take a box, and then within the box, you can place your antenna. The box itself is sitting in an anechoic chamber, and you have receiver antennas outside, and you're measuring the radiation that basically is escaping. The other system we used is it's an anechoic chamber that actually has a hole cut in the side with a mounting fixture, and we actually put the panel there, and then the antenna is outside. We have one outside and one inside of the anechoic chamber. So you're looking at the transmission essentially through that window. So that's the two basic techniques that we were working with, both of which require some work to begin with. When we dealt with a small box and the antenna within the box, there were some issues in terms of the cabling becomes very sensitive. You can actually move the cabling, and you can actually affect your readings. When it comes to the anechoic chamber approach, you have to make sure the edges are well sealed. That kind of information, if you want to contact us, I'm sure we can share that without a problem, because that's just some basic standard techniques that we've been using for measuring. We've also, when it comes to the structure ones, the structure itself is placed in an anechoic chamber, and then it's treated much like the box. Antenna inside, one outside, and then you measure the loss across.
Gotcha. Great. No, that helps definitely elaborate on the testing. We had, let me ask one question that looks like Elena has asked, and then looks like has a hand up as well. So I'm going to see if I can unmute Elena to kind of follow up maybe. But the initial question as received says, will EM shielding make the vehicle invisible to the enemy's radars?
No. What it'll do is the EM shielding, by reducing the electromagnetic shielding for those systems that actually detect a vehicle based on electromagnetic output, if you will, the answer there is yes. But will it reduce it from an aspect of radar signature? The answer is, I want to say no, but I'm going to say not necessarily. We currently have a program where we're looking at that. As it turns out, the way the electromagnetic shielding that we've done, that works almost as a perfect ground plane. So we're looking to see if we can now build on top of that to then get a reduction in radar signature, and then also still maintain the electromagnetic shielding.
Okay, gotcha. And you might have just covered this, but the follow-up question there was, will the EM shielding obscure the signature of the combat vehicle?
The EM shielding, it will obscure it only from those systems which are used to detect electromagnetic emanations from a vehicle. It's not going to do it just from a radar aspect.
Okay. All right. Sounds good. And then let's see, what other questions? We got questions about the copper mesh layers. Two questions asking about the grounding. Are Are those copper mesh layers grounded or are they floating?
They are floating within the material. What happens is they are placed in without any additional resin system. So the way we are looking at it is you have the intimate contact between it and the graphite. So while they're not grounded, there is some connection, if you will, between all the different layers, but they are free floating within the composite.
Okay. And then the question related to that is, are there any grounding concerns or recommendations?
We have not had any. I know our customers haven't seen any in that regard as well, but one of the next steps that we would like to get to is actually work this up in a full electronics bay. The idea here is that you would use a lot of the same material for the electronics bay, and that would help with the grounding. Keep in mind too that the copper mesh is often used for lightning strike, and it is used as a grounding medium, so that when lightning would strike a vehicle, it's designed to have an attachment point and an exit point. My point being is that you can actually create those grounding planes within the structure, depending upon how it's going into the vehicle itself.
Gotcha. Let's see. One question was asked if have you tried a combination of conductive fillers?
We have not tried the conductive fillers as of yet. One of the things that we're looking for, which is for radar cross section, however, is we're looking at the introduction of some what you would call fillers, to see what that does to the system itself. We have considered it. We just have not pursued it in that regard. This is like the first step, I'd like to say, for the shielding, because we want to push it even higher than what we currently have. So we're trying to see where we go. And that was one of our thoughts, is whether or not we could, I'll use the term, dope the system with even some additional material, or perhaps even put in discrete layers of the peak resin that might be filled. So we've been considering that, but we have not pursued that as of yet.
Gotcha. And then I'm going to go ahead here and try to unmute Elena. She said she'd like to follow up with the questions. Let me see if this works. Request is sent. All right. Looks like you're live, Elena. I'm not sure if we can hear you, though.
Hello.
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 Yes, we can hear you. Go ahead with your question if you have a follow-up.
Okay. Just a second. So you can hear me now, yes?
All
Yes.
good. Yep.
Okay. So my question is, I have a contractor who is developing a shielding device using shielding panels using metamaterials, and these panels will absorb basically microwave radiation. Fairly a large spectrum actually of microwave radiation. I think their purpose is, to obscure the signature of the combat vehicles, from the point of view of radar detection, but it could be also, a possibility to protect the device on this combat vehicle from electromagnetic radiation, like high power electromagnetic radiation. So my question actually was, can we do both? Can we obscure the signature of, because the proposal, the solicitation of the CBERS was for the proposals to, manage the camouflage system, metamaterials to manage the camouflage of the combat vehicle. But the proposal that received an award actually is called hierarchical nanocomposite metamaterials for shielding of combat vehicles. So can it do both? electromagnetic shielding and, you know, signature management?
Okay, look, I think I can answer that in this regard. The customer that we have sure hope so. What the issue has been is your radar signature, if you will. Typical ways of reducing that radar signature happens to be typically, let's say, with Magram. And the other one, which I'm more familiar with, is it uses a printed honeycomb core. So what happens is your outer layers are transparent, then it runs through a thickness, if you will, of varying intensity of carbon particles, which then absorbs that energy before it hits the back plane, which is a reflective surface, and then basically it comes back out the other way, some more absorption, and you get a lower return signature. So in the regard of electromagnetic shielding is concerned, if you build that ground plane, so it provides your electromagnetic shielding, then you look at the difference between that ground plane and your outer surface as the area of which you can then try to treat the radar. You know, because once the radar hits that ground plane, it's going to reflect back out. There's just no ifs, ands, or buts about it. It's just coming back. So you want to use that space in between the two. And the one area that has been lacking in terms of research, if you will, has been what can you do in the thickness, if you will, of a laminate. When we're dealing with very thin plies, we might be dealing with 12 plies of material. There's not a lot of space to work with. So if the material that they're working with can create that effect over that short distance, the answer would be that, yeah, you can get it, but you're not going to get something that does both. So you're going to have to take electromagnetic shielding and take the radar reduction, and then you have to then, if you will, laminate the two of them together to get the combination effects. Does that make sense?
Yes, but what were the numbers that you mentioned for the distance between these two layers?
The two layers that we've been dealing with, we're only talking about a handful of plies. It's tape material. That is something that we would have to get offline. That's part of the design. We'd have to get that released by the customer. But we could share the actual laminate. But you're only talking about a few plies of material. And when we're talking about structures in general, when you talk about the honeycomb core approach, that was maybe about for the Comanche, I want to think that might have been about an inch thick. They found to be sufficient. But when it comes to composite laminate, we just haven't seen anything. Like I said, we are hopeful that some of the materials we're going to be looking at will provide that reduction in signature. But right now, we're just in the process of developing what those layups would be. But you're not going to get something, at least to my knowledge, you're not going to get something that does both, or you're going to have to construct a laminate where, almost like a layered laminate, where you have the one layer, which is going to be your shielding, and then based on top of that, you want the section that's going to reduce your radar signature.
Okay. Yes, they have a layered approach, by the way. My contractor, they do have this layered approach. So one for microwave, one for infrared.
There's also a technique out there which we're hoping to explore as well. It also deals with actually doing almost like a printed circuit in the individual layers to work as a means of absorbing some of that radar. The basic technique for a lot of it, at least for the carbon fiber, is that as a radar wave comes in, it vibrates the carbon particles, is turning the electromagnetic energy to heat, and then that's dissipated away.
Yes.
That's the main principle behind that. So
yes, I forgot to mention my contractor, they do absorbing of these microwaves and then dissipating using this some infrared dissipating layer. Okay.
Right.
Yes. Okay, thank you. So I've got the idea. Thank you very much.
All right. You're welcome.
Thanks, Elena. I'm gonna go ahead and mute you, and we'll carry on with the last couple questions here. So thank you for that question, though. All right. So the last couple questions here, Rick, were about some of the design. Let's see. We had one question asking why use a copper grid instead of an inhomogeneous layer? Are you looking at minimizing reflections besides shielding?
Well, we actually a couple of things. It's an expanded copper mesh is what we have in there, and the expanded copper mesh, we want to maintain the structural properties. So even though some testing that I've done in the past where I've put an individual layer of copper in there, we know that if you do that, you're going to have a bigger effect, if you will, on the structural properties for one thing. The other aspect is we're also looking at the copper mesh as a way of filtering out some of the radiation, actually taking advantage of the mesh itself. There is data that shows that different mesh configurations or sizes can actually have an effect on that radiation and can give you some benefit to the shielding effectiveness.
Gotcha. Okay. And then a couple questions here maybe about future work. One is asking if that shielding technology would be applicable to personnel protection.
It would be applicable for personnel, not so much from a, yeah, I want to say not from an aspect of clothing, if you will.
Sure.
Although there is some effects that you might be able to make a vest or something out of the dry material, but that's not something that we've been looking at. But as far as personnel protection, we have thought about this for, you could have buildings and things like that. You can make flat panels. You can actually build into a protected structure, if you will, which the individual could be in for whatever their purpose is.
Okay. And then the other question about future work is what this might do with respect to thermal properties for cooling.
That is one of the areas that we are exploring. If you look at it from the graphite aspect itself, it's the more conductive a material. It doesn't matter whether it's electrical or heat. It does both quite well. We know graphite does conduct the heat away very well, but we haven't gone as far as to the installation of electronics into the system to see what impact we actually have on the heat dissipation. In a metal structure, you might have cooling fins that put in there. You might have fans that go in there, and they are all, when we're talking about looking at the penetrations and venting, if you will, that's what we're actually targeting that for, to make sure that we have a good means, if you will, of dissipating the heat.
Gotcha. Okay. All right. Well, I think that kind of tapped us out right at the top of the hour, and sounds like a dog got alerted anyway. So, Rick, thanks for the time. Thanks for everybody for joining us. We're going to go ahead and end it here. Again, if you have any further questions, please reach out to Rick. His contact information and email is on the cover slide, which are available on the webinar's webpage. You can always reach out to DSIAC, and we'd be happy to help answer some questions or get you in touch with Rick. And otherwise, just have a great day. And thanks again, Rick.
All right. Thank you.
Yep. Take care.